So, in the last video we have seen how to solve boundary value problem, initial boundary value problems for the heat equation in infinite domain as well as semi infinite domains. We have shown that the solution exists, we have actually constructed the solutions in all these domains, and then in these unbounded domains, either fully infinite or semi infinite domains for the one dimensional heat equation. We also have seen that the solution is unique, that is what is shown. So, solution is we have a unique solution for all these problems whatever we have considered so far for the heat equation as well as the wave equation, that whatever we have considered in the earlier videos. So, a problem, a boundary value problem, either is a initial boundary value problem or a boundary value problem, that is well defined if the solution exists and it is unique, and also there is a condition that is called if you have whatever the initial data and boundary data, you perturb little bit. So, this is what is the data you are given. You are given a data, that how do you find the data? That is normally practically you can get the data at time t equal to 0, or on the boundary you can calculate, you measure it and try to see it, try to get the data. That data when you try to get it, that may not be exact data. So, it may be having some small error, very little. So, you may have an error may be very small, but it is not certainly the exact data, exact boundary data. So, even if it is not exactly the correct boundary data, even if you perturb little bit, so that means you take boundary data with a little error. Suppose fx is the boundary or initial data, you take some f tilde that is very close, let us say this distance, this maximum of this wherever this x belongs to the domain, okay. So, let us say if this is very small epsilon is positive, if such a thing instead of fx, exactly fx you have the solution, okay. Correspondingly with this initial value fx, you have a solution u of xt. Now, if you calculate if your initial data is f tilde of x, that is very close to f, but it is not exactly f. In such a case, you have a solution, let us say you know how to find the solution, that is say u tilde of x of t. So, you change the initial data that is very close to the actual data. So, then you have a different solution, and then a problem is well defined if the whatever you found these solutions are also very close, they are also very close to each other. So, let us say some epsilon, some delta, okay. So, the delta depending on epsilon. So, okay, so you choose your data very close to f, then correspondingly your solution also will be close to those solutions are also will be closer to each other. So, this is called continuous dependence on the initial data or the boundary data. So, once this condition is also satisfied, then you say that the initial boundary value problem or initial value problem is well defined. So, for all those problems whatever we have done, this can be done. This you change the initial data, you perturb the initial data, and still you can see that corresponding solutions will be close to each other. That analysis we do not do in this course. So, you can assume that that is also true. So, all these boundary value problems or initial boundary value problems or initial value problems, these are all well defined in that sense. So, that is what we have seen in the last few videos. Today we will have a heat equation, we will have a solutions for the heat equation in a finite domain. So, one dimensional heat equation we consider, and we consider over a finite domain. So, that is associated with this finite rod. So, you take the finite rod that is heated initially, insulated laterally, and it is heated. Initially you have a temperature u at x0 equal to some fx. So, initial data you have, now you have the boundary here. So, at these points you have a boundary, you can provide the temperature. So, you fix this boundary data saying that at x equal to 0 and this is L, 0 to L is the distance. So, this is the length of the rod, L is the length of the rod. So, you have 0 for all time, you maintain some temperature, let us say T1. Here also at this end you also maintain u at Lt for all times, you maintain a temperature T2. Then we can find the solution for all times in this rod, how it diffuses. When you maintain the temperature T1 here, T2 here, initially a rod is at the temperature Fx. So, let us write this initial boundary value problem, initial boundary value problem. So, let us write this first. So, this is the heat equation, satisfies the heat equation. So, you have the temperature satisfies the heat equation. U is a function of x and t, ut minus alpha square is a constant, and then uxx equal to 0. Now, x belongs to 0 to L and t is positive. So, in this domain, so that basically if you say x and t, this is your t, x is this, x is at 0 to L. So, you are in the actually in the kind of strip, you are in this, this is your domain. So, this is your domain. So, t is positive and this is between 0 to L. So, this is your domain, this is your domain. So, in this domain this heat equation is satisfied, and you have the initial data is u at x0 is fx, and boundary data is u at 0 t equal to t1 and u at lt equal to t2. So, how do we solve this one? So, this is what what we do is we try to break this problem into this initial boundary value problem into two problems. How do we do this? A solution, let us see. So, basically if I can do, see, if I want to extract a Sturm-Liouville problem, you need the boundary conditions to be homogeneous. That means I need these boundary conditions to be 0. So, in order to make it 0, I break this solution u as let us say, let us use I want a u of xt as some v of xt plus let us say some g of x, only x. Okay. So, this is a trick. So, you just try to break this into two problems. So, in this, once you break this satisfies the heat equation. Okay. So, if you impose that, so let let u be this such that v satisfies heat equation, v of xt satisfies heat equation. Then that is Vt minus alpha square Vxx equal to 0, x belongs to 0 to L, okay, and t positive. So, this is what is the domain, and then what happens? So, if since u also satisfies the heat equation, v is satisfying the heat equation, then g should also satisfy the heat equation. So, g is a function of x, when you put it in the heat equation it becomes gt. So, time derivative of g will be 0. So, you have minus alpha square gxx is also 0. Okay. So, that means this is simply function of x. So, g double dash of x equal to 0. Alpha square is constant. So, this cannot be 0. Okay. So, this implies you have this g double dash of 0. So, again the domain is x belongs to 0 to L. So, this is what happens for v, this is the equation, for g this is the equation. Now, you look at what happens u at x 0 is fx, okay. And now, let us first apply these boundary conditions. If you apply these boundary conditions, if you put x equal to 0, here, u at 0 t is t1 which is equal to v at 0 t plus g at 0. Okay. So, I choose now again I choose here v0 t as 0. Okay. So, choose v of 0 t equal to 0. So, once you see this immediately, then once you choose this, if I choose v of 0 t is 0, then g of 0 is t1. Okay. Boundary condition 1 gives you that, gives me this one. Now, you do the same thing for boundary condition 2, that is u at lt, that is t2 here. Okay. So, t2 equal to v at L2 lt plus g at L2 g at L. Okay. So, now again I choose, if I choose v at lt as 0 for every t, then g at L has to be t2. Now, we just combine what you have. So, what you achieved as actually, now you write the problem for v satisfies the heat equation V satisfies this boundary condition, this boundary condition. And what happens to the initial condition? Initial condition you can easily see. So, before you give the we find the initial condition for V first. So, V is not completed, okay. We know only heat equation and some boundary conditions like this. These are the boundary conditions what you have, okay. So, I have a boundary conditions here, this is the one and this is the one. So, you have two boundary conditions and heat equation what we have for V. But for G I have this ODE, two derivatives is 0 and G, this is one condition and this is another condition. So, that solves, okay. So, you write first G dash of x equal to 0 if x is between 0 to L and G0 is T1, G at L equal to T2. So, this how do I solve? So, we can solve this. So, what is the G double dash of x? So, if you simply integrate, G of x will be some arbitrary constants into x plus C2. C1, C2 are arbitrary constants. X is between 0 to L, C1, C2 are constants you can find. So, apply this boundary data. So, G at 0 equal to T1. So, this will give me C1, C2 equal to T1. And now what happens? So, immediately what you get is G of x is C1x, now C2 is T1. So, that is what you have. Now, you write, now you apply the other boundary condition. So, G at L equal to T2. So, this will give me now this is your general solution. G at L, that is C1 at L plus T1 equal to T2. So, this gives me what is my C1? C1 is T2 minus T1 divided by L. So, now you go and substitute into this to get. So, this immediately give me what is my Gx. Gx is C1 is T2 minus T1 by L x plus T1. This is what you have. So, this is by Gx, x is between 0 to L, satisfying these boundary conditions, okay. Now, you apply your initial data u at x0, u at x0 is fx. So, if you apply initial data here, okay. So, u at x0 is fx, fx equal to initial condition will give me u at x0 equal to v at x0 plus gx. So, this I know already now, okay. This is what is gx. So, this implies now I have v at x0 is u at x0 is fx minus this gx is this one, okay, minus gx. Gx you can write if you want. So, T2 minus T1, this is given known into x minus T1. So, this you call some f1 of x just by definition, okay. This you can define as a definition. So, this is your V here. So, now I know what is my G. Now, I know what is completely G. V I do not know. V is actually now satisfying this heat equation, this boundary conditions, now this initial condition, okay. So, let me put this problem. So, what you have is Vt minus alpha square Vxx equal to 0, x is between 0 to L, V at x0 equal to f1 of x. F1 is known now because f is given, T1, T2 are given. So, this is this function I know, L is known, L is given, right. So, this is the length of the rod. So, we have f1x. So, between 0 to x is between 0 to L, and then boundary conditions are V at 0 t equal to 0 now, okay. These are 0, this is how I have chosen, equal to V at LT. So, this is what it has become, initial boundary value problem 2, okay. If you call this as 1, if this is 1, now the initial boundary value problem 1 you want to solve, that you reduce to initial boundary value problem 2. So, that is easy to handle because now I have the boundary data which is 0 homogeneous boundary data, okay. This is true for every t. So, this is what we solve by the separation of variables method. So, we will solve this, we solve for v of xt, we solve rather I initial boundary value problem 2 by separation of variables, because the boundary is finite, Okay. So, the domain is finite. So, you can easily say, so look for a solution like this form. So, V of x t as x of x and t of t as a non-zero solution, because you can only say I am only now looking for the solution of the equation. So, because it is a homogeneous equation, you can always look for 0 is a solution. So, but I am looking for non-zero solution. Okay. So, you look for non-zero solution, then you simply substitute V t in this form x of x t of t into the equation. So, you get x of x t dash of t minus alpha square x double dash of x t of t equal to 0. Okay. Now, because this is non-zero, I can divide both sides with I can divide both sides with x by x v of x t, that is x of x into t of t. So, that will give you t dash of t by t of t. Now, I bring this alpha square here. So, alpha square equal to, now if you, this one will be x double dash of x, t of t will go. So, x of x will remain here. Now, the left hand side is function of t, this is a function of x. Okay. So, that means it has to be constant. So, that is what you have. So, now the partial differential equation, that the heat equation becomes two ordinary differential equations. One is x double dash of x minus lambda x of x equal to 0. X is, the domain is again 0 to L. This is a finite domain. This is where, this is how I extracted the Sturm-Liouville problem, Sturm-Liouville type. Okay. And what is the other one? Other one is this one. So, this will give me t dash of t minus lambda alpha square t of t equal to 0. Okay. So, apply the boundary condition now. If you apply the boundary condition, so if I apply boundary conditions, v of 0 t equal to 0 gives x of 0 is 0. V at L t equal to 0 gives x at L equal to 0. So, this is what is the problem now. This problem is your Sturm-Liouville problem, Sturm-Liouville regular Sturm-Liouville problem. So, this is how you extract it. Okay. So, this is your regular Sturm-Liouville problem, is already in the self-adjoint form. So, this is what we know. This is x dash, p is 1, this is dash, that is x double dash, q is 0, okay, plus 0 times x equal to lambda times 1, w is 1, and here x of x means x of x. So, this is what x of x, you can write x of x, x dash of x. This is actually x belongs to 0 to L. So, it is already in the self-adjoint form. Once it is a self-adjoint form, you know that it is the eigenvalues are real. So, it is already self-adjoint form, or right, Hermitian form, it is a Hermitian form, right, self-adjoint form. So, implies lambda is real. Lambda is real means immediately lambda is either mu square or lambda equal to 0 or lambda equal to minus mu square. So, we look at these three cases. So, first start with the lambda equal to mu square. Lambda is mu square. So, what you have is this equation. So, x of x, the equation is x double dash of x minus mu square x of x equal to 0. And then with the boundary condition, x of 0 is 0, x of L equal to 0. So, this one, how do you find the general solution of this is C1 e power mu x plus C2 e power minus mu x. Now, you apply x of 0 equal to 0 will give me C1 plus C2 equal to 0. So, this will give me C1 equal to minus C2. So, this implies x of x is C1 is minus C2. So, you have a C1, take it out. So, e power mu x minus e power minus mu x. So, you can say this is 2 times, that is sine hyperbolic mu x. Okay. Now, you apply at xl equal to 0 will give me for this now the general solution is this. Now, we have a 2c1 sine hyperbolic mu l equal to 0, because sine hyperbolic function is 0 only at 0, mu l equal to 0. Mu cannot be 0 since mu is positive. Okay. mu square is positive. So this is with mu positive. So mu is always positive. So it cannot be 0. This is non-zero. So implies C1 is 0. So C1 is 0. C2 is, once C1 is 0, C2 is also 0. Okay. Immediately what you have is the general solution becomes completely 0 for every x. X belongs to 0 to L. Implies lambda equal to mu square is not an eigenvalue. Okay. So you can also do for lambda equal to 0. Let me test lambda equal to 0. In this case the equation becomes, so this equation becomes x double dash of x equal to 0. So you have x of general solution of this is C1 plus C1x plus C2, and then you apply x of 0 is 0 will give me C2 is 0. So this is gone, and then x at L equal to 0 will give me again C1 L equal to 0. This gives me C1 is 0. So that means this is also 0. So implies completely 0. X of x is 0 implies 0. Lambda equal to 0 is not an eigenvalue. Okay. So that means there is no non-zero solution for this problem with this boundary condition. So with this lambda, now we are left with only lambda equal to minus mu square. So this will give me these eigenvalues. So you have x double dash of x, you have a plus mu square x of x equal to 0, x is between 0 to L, x of 0 equal to 0 which is x at L. So what is the general solution here? Because this is minus mu square, if you look for e power I k, e power k x kind of solution, it will become k is plus or minus I mu, so that you have e power I mu x and e power minus I mu x. They are linearly independent solutions. So similarly if you add and subtract, you will see that sin mu x and cos mu x are solutions. So you have a general solution is C1 cos mu x plus C2 sin mu x. Now you apply these boundary conditions, x0 is 0 will give me, so apply the boundary condition, this gives me C1 C2 into sin, that is 0. Okay. So C1 equal to 0. Okay. So this immediately x of x is nothing but C1 cos, C1 is 0. So what you are left with is C2 sin mu x. So this is what is the general solution. Now you apply other boundary condition. So if you apply the other boundary condition, that is x at L equal to 0 will give me C2 times sin mu L equal to 0. So sin function can be 0 for certain mu values. So here mu is positive, and so C2 for those mu values for which sin mu L equal to 0, C2 can be arbitrary. That means sin mu x such that mu is satisfying sin mu L equal to 0 will be eigenfunction. Okay. So you can see that sin mu L can be 0 implies either C2 is 0 or sin mu L is 0. C2 is 0 means completely 0, x of x is completely 0, it is not an eigenvalue. Okay. But there are certain mu values for which sin mu L is 0. So sin mu L is means mu L equal to n pi. Okay. Mu is always positive, so n is running from 1 2 3 onwards. So this implies mu is n pi by L, n is from 1 2 3 and so on. By the way, I missed something here. So when as soon as you write this in this form, immediately you can see the dot product of these functions here. Okay, solutions, dot products of the solutions of this. Let us see some phi and psi. Dot product I can define as dot product is defined as integral 0 to L. W is 1, so there is no weight function, and you have a phi x psi x bar dx. Because these are all real, so eigenfunctions also will be real valued functions, so bar does not matter. So that is what is this. So now you have this, these are for these values, you have sin mu L is 0, C2 can be arbitrary, implies lambda equal to minus mu square, that is n square pi square by L square is an eigenvalue for n is from 1 2 3 and so on, and the corresponding, so because it depends on n, let me call this lambda n, and corresponding solutions, let us call this phi n, okay, phi n's or xn's, let us say xn's, xn of x, these are the eigenvalues. That is, when you have when you put m equal to n pi by l sin mu x, so sin mu is n pi by l x, sin mu x, okay. This depends on n, so I am putting xn, x of x as xn is eigenfunction, is an eigenfunction, eigenfunction corresponding to this lambda n. So, for n is, so in both the cases n is running from 1 to 3 onwards. So, now we find this eigenvalues and eigenfunctions. So, I know what is my x for these two problems, okay. I have one problem here, I have another problem here. So, for this I know the eigenvalues and eigenfunctions. So, I have xn that satisfies. So, that same lambda you can put it here. So, what happens, t dash of t minus lambda is minus mu square. So, plus mu square. So, mu is n square pi square by l square, t of t into alpha square is there, into alpha square, okay. So, lambda into alpha square. So, I put this lambda into t of t equal to 0. So, this is first order ODE, linear ODE. So, I can solve it directly. So, the general solution of this is, so this see, because it depends on for each n is running from, I replace this lambda with the lambda n. So, I call this that ODE for each n I have a different each ODE, okay. Corresponding to n I have one ODE satisfying this, I have a ODE. So, I can say that Tn of t, that is some arbitrary constant a n, depends on n, okay. Fix n, a n is fixed. So, a n times, so a n is corresponding to that ODE arbitrary constant, a n times e power minus n square pi square by l square alpha square t. Does it satisfy? You differentiate n square pi square alpha square by l square, okay, and this will be this, minus of that will be there. So, this will be plus, so 0, okay. So, this is your solution. So, this is the solution, is the solution above ODE. So, now what you have, so for each n my v of xt for each n depending on n. So, I am calling this Vn as xn of x into, that is sin n pi x by l into this Tn of t, that is a n times e power minus n square pi square by alpha square by l square into t. So, this is what you have. Now, I take this sum. So, this is a solution, this is a solution satisfying heat equation with boundary conditions clearly, right. So far this is, each of this is satisfying the heat equation with boundary conditions. So, I superpose all these solutions for each n, okay, n is running from 1 to 3 onwards. So, if I superpose these solutions, this sum is also, I can assume that is a solution, that you call it V of xt, V of xt as a superposition of all these solutions. N is running from 1 to infinity, that is n is from 1 to infinity a n sin n pi x by l e power minus n square pi square alpha square by l square t, okay, as a superposition be the solution, Now, this solution, because as a superposition you assume that, suppose this is a solution, superposition we can actually show, once you get these constants, one can show that it actually converges uniformly. So, that means actually you can assume superposition principle if you apply, this is the solution. So, you can assume that this is the solution that satisfies the heat equation with the boundary condition. Now, you apply the initial data, that is initial condition is, so far we have not used. So, V of x 0 equal to f1 of x, f1 of x is fx minus g of x that you have evaluated earlier. So, implies V of x 0 is this sum, n is from 1 to infinity a n sin n pi x by l. This, when you put t equal to 0, that is 1. So, this is equal to f1 of x. Now, sin n pi x, these are all eigen functions, these are xn of x. So these are all these are orthogonal, these are complete orthogonal set, that is what from the Sturm-Liouville theory. So this implies I can get my an, this simply multiply the same eigen function and integrate. So that means you take the dot product with the eigen functions both sides. So you can see that integral, so in dot product with f is f1 of x right hand side, f1 of x into sin n pi x by L dx divided by integral 0 to L sin square n pi x by L dx. Okay, that is what remain. Now this is from n is from 1 to 3 onwards. So this solution Vx, this is the solution where with an's are this is actually now satisfying heat equation, boundary condition and the initial condition. Okay, this is the required solution. So this is what is we need. This is how it behaves. You can see physically as t goes to infinity. Suppose you have a rod that is initially at some temperature and you maintain constantly at T1 and T2. Okay. So what happens? Eventually, even though you maintain the temperature T1 and T2, what happens to V? V solution is, by the way, V solution is boundary terms are 0. Boundary you maintain at temperature T 0, 0, 0 here, and as T goes to infinity after some time, and the whole so temperature of the rod becomes cooled down. So it's once a heated rod and both the ends everything is insulated, even the you maintain both the ends of the rod is at the temperature 0. Then what happens? Slowly heat diffuses and finally temperature will become 0. That is what you see as T goes to 0. As T goes to infinity, that means for larger times this is going to 0. So that means finally V of xt is 0 for all times. Okay. So you can see that remark is V of xt as limit t goes to infinity is actually 0. So the rod becomes cool. Okay, it becomes at 0 temperature. This is what is V. So actual rod is what you have is this is at T1 and T2. This is at T2. So what happens? V is 0. What is your solution is V of xt, that is this solution, and plus g of x, that is what we have. So as limit t goes to infinity and this limit t goes to infinity and this is nothing but this is 0 plus gx. So this is equal to gx. So what is gx? Gx is simply, so this reaches the steady state. So T1 is here and T2 here, in between you simply have a steady state solution. So T1, so linearly it varies. So this is a linear function, g is a linear function, that is what we have seen. So what is a linear function? You can see if you look at the g is when you put x equal to 0 it is at T1, at x equal to L it is actually T2. So it's linearly varies, one is at T1, other one is at T2. So that is what is your gx function. So once you have this, the eventually as t goes to infinity, if you maintain your rod at temperature T1 and T2, eventually as time goes to infinity, you see that the temperature simply rod will have a temperature maintains linearly. Okay, this is what you get out of this. So it has two problems. One is temperature of a rod, finite rod, we want to find out for all times when you maintain at the two different temperatures, one end at T1, other end is at T2. Okay, yeah, so this you convert into a problem with both the ends you maintain at 0 temperature. Okay, so 0 temperature if you work out, so worked out. So this is what you actually solved, and that actually finally solves rod which you maintains at the temperature T1 and T2. Okay. So you have both the problems are combined. So if you are given at two problems, either of the problems, one is a problem with both the ends are at 0 temperature, or you are given at a rod with two different temperatures at both the ends. So both things you can solve now. Okay, if you are given two different things, you convert into 0, 0 type by this technique, convert a boundary value, initial boundary value problem 2, and that you solve. That is what is at 0 degree. Okay, 0 degree at both the endpoints. So this is how you can solve this. Now what else we can do with this rod? The rod is if you are given a rod, this is insulated and you have a boundary condition, finite rod, and you have a initial data u at x0 is equal to fx, and you can also insulate. What you can do is you can insulate one end and you can allow it to be say some, you can maintain some temperature U at L T is say some T, some temperature, let us say some T1. Okay. Here you say this this is insulation, means you are not allowing the heat to go out, that means the flux, that temperature normal derivative of the temperature, that is Ux at x0 for all times you maintain 0. So, if you insulate it, this is the condition you have. Okay. Or you can simply interchange, or you both can have. So, both can have. So, both sides if you insulate, you do not allow the heat. Initially the rod is at some temperature, you are not allowing, everything is, so all heat will be inside, and you have Ux. This side also if you insulate Ux, what do you expect? You expect whatever the distribution of this temperature here, that will be after some time it will reach to steady state. Okay. It will reach steady state, that is what should be the solution. So, this if you solve, we can solve this in the next video. Okay. And also this is what we will see in the next video, and we can also make one more problem. So, we take the same rod, you allow the heat exchange, you if you allow the heat exchange at the boundary, that means the flux is proportional to the temperature, that means Ux plus some constant k times U equal to 0. So, this is the boundary condition. The mixture of U and Ux will be the boundary condition here. Similarly, you can also make here Ux plus k some constant k2, here k1 k U equal to 0. So, if you keep this boundary condition, you can also work out the same way. So, only thing is boundary conditions are all having 0 0 boundary condition. Okay. So, you have a homogeneous boundary condition, that is what is required for the Sturm-Liouville problem which you want to extract. Okay. If they are not, you have to use the technique that we have seen in this video initially. So, you try to write the problem U equal to V of xt plus some g of x. Okay. For g you give these non-zero boundary conditions now to g and 0 boundary condition to v, but initial condition. So, once you solve this g, you can initial condition for v will be different, that you can solve it. So, these are the 3 things. So, 2 different kinds of problems one can look at it. So, we will try to see one of these, maybe we will do this one. So, both the ends are insulated, or you maintain one at the insulated, other one is maintained at some temperature. All these things you can work out. Okay. We will try to see the next video when the temperature of the rod when initially at some temperature along the rod and both the ends are insulated, what is the temperature for all times. This is what we will see in the next video. Thank you very much.